be less in this case, and in this case, gain will be more gain you can have it. So regarding noise performance, this first one is preferred. Coaxial performance, whenever gain is equal, high gain required, then the second architecture is preferred. And also we can have dual pumping. You see third ones that where both co-directional and counter-directional pumping are used. Right. So both the advantages you can have it in this case. Noise performance as well as gain, both the things can be achieved in this case. And you see power conversions, efficiency power amplified signal is power. From here you'll get the power. You'll get actual power. You will get the power from the pump energy. And pump energy is, if you see the conservation energy, that is output signal, that will be actually input signal plus these the pump signals. You see this ratio will be lambda p by lambda s. That is the lambda p is a pump wavelength and lambda s is signal wavelengths. Since pump energy is more, so lambda p will be less. That's what it is mentioned here. So h nu p energy more means hc by lambda. So lambda will be less, then h nu will be more. That's what it is here, right? So signal wavelength, signal power sooner never it will exceed the pump power, but signal wavelengths is greater than the pump wavelengths. And also another important is this that just I mentioned, input signal always it is less than the pump, but the energy is extracted for amplified amplification purpose, energy extracted from the pump signals. And the conversion efficiency in this context, it is actually output signal minus input signal with the pump signals, which since pump input signal is very less compared to the output signal, so we're going to signal output by signal pump power input, that is actually lambda p by lambda s, that is conversion efficiency general maximum can be I see it is 1. Always generally it is less than 1, right? And also another thing is this, sometimes quantum conversion efficiency is used. You see that is related to the pump the power conversion efficiency. In this definition is this lambda s by lambda p into PCE. And here also maximum conversion efficiency can be 1. Right? So the gain factor, gain, output by input for any gain, output by input, that you can write it P as PS signal output by signal input. That is from the previous conservation of energy that we have seen it 1 plus lambda p by lambda s pump input by signal input. So signal input power always less than the pump input. But if it is very high, then you see if it is greater than this ratio lambda p by lambda into p input, if this one it is greater than this one ratio, that times you see that times this term will be neglected. If it is very high, that means something divided by very high, it will be 0. So this will be neglected, and so only 1 gain will be 1. That means device will act as a window. So output will be equal to input. Right? Device will be act as transparent. So for the maximum gain, always input signals will be less, and that is the condition. It is lambda p by lambda s into p pump input by g minus 1. That is from these conditions. Also, gain depends upon the length of the fiber. That is maximum gain you can have it rho times sigma E times L, where rho the rare earth element, erbium ions, etc., erbium, ytterbium, etc. So it depends upon these rare earth element concentrations, depends on the emission cross sections and length, right? So combining these two relations, previous and these ones, also we have seen this depends on pump power, etc. Depends on the length also. So maximum gain can be achieved when you consider the minimum of these two expressions, this one and the previous one, these ones, and the corresponding maximum power also will be minimum of this one and minimum of these ones. They are the important relations while dealing with the optical amplifiers. This you can have it in the Kaisers. And these things, if you just plot it, what you'll see it, gain versus amplifier length, you can see it here. At certain length, for a certain pump power, gain will be maximum. For a particular pump power or particular length. If you increase the length, gain will fall. Even if you increase the pump power, then also certain time gain will be maximum, but it will fall. Right. So pump power, this is gain versus amplifier length. So at a certain length, for a typical pump power, the gain will be decreasing. So it will maximum, say it is 4 milliwatt pump power, gain can be maximum above 30 dB. But after that, gain will fall. That is because that times there will be no excited carriers in the upper energy state. Similarly, if you plot it output signal gain versus output signals, you can see it here. Output signal powers after certain power gain will fall. Right. So these are the uh, important curves while dealing with the optical amplifiers. Next, you see the switching element. Switching element, so far we have seen the optical amplifiers. Similarly, optical amplifiers is the replacement of repeaters. I told you repeaters, there can be optical to electrical conversion, next there will be amplification, receiving, etc. Those things will be there. After that, again, conversion will be there from electronic to photonic conversions. Similar things are there in the switching elements. Nowadays, I mean, most of this nowadays trend is to get all optical switch. Existing switches, most of the existing switches are now based on electronic switch. So fast optical to, in that case, optical to electronic conversion is there. Next, switching is done. But here you see, I mean, here of course in electronic domain, if you just do the switching, which is existing now, most of the cases, then you can have great flexibility and also a great flexibility in terms of switching and routings, right? But you see, here the disadvantage will be there, since once you do the conversion, the speed will be less. Once you do any conversion, delay will be there. So switching means speed is most important aspect for any kind of switchings. So trend is to get all optical switchings, just like all optical amplifiers. So high speed networks, if you want to do it, then you need all optical switchings. So let us see what are the switchings, what are the switching elements that can be used in the optical domains. At present, most of the switches are being operated in the electronic domains after optical to electrical conversions. You see it here, optical switches, they can be of two types. They can be either relational devices or can be logic devices. Relational devices here, actually in these devices, a relation is established between the input and output, right? And that relation is a function of the control signals. Relation is established first, input and output, and that relation is a function of control signal that is applied to the device. And that relations, it is independent of the contents of the data, right? So this relation cannot change the current. I mean, here not the relation, information that is entering into the device cannot change these relations. So example is directional coupler. We'll see different types of devices. So relational devices, the main thing is this: a relation is established between input and output, and this relation is a function of control signal which is applied to the device, right? So in this context, these relations cannot sense the presence of the individual bits. So some flexibility is not there here. Independent data cannot be switched. And data stream cannot be switched independently in this case, right? Of course, you can have this data transparency in relational devices, but flexibility is reduced in this case. So here switching facility is obtained through some relations where relation is a function of the control signals, and it is useful for circuit switchings. But there are another kind of switches are there where the in the information carrying signals, information which is entering into the device, that can be used to control the state of the device, right? In such a way that some Boolean functions can be performed. So here the information carrying data can control the state of the devices, and it is very useful for packet switchings. Right here, some extra facilities, extra flexibility, we can have it with this case. One thing is quite clear: relational devices are used for circuit switchings, and logic devices are used in the packet switchings. So let us see some examples of these switches. Then these switches can be implemented using optical cross-connect elements. Optical cross-connect elements. Fiber, generally these are based on optical fibers, optical cross-connect elements, and you can see it here. This is 2x2 cross-connect elements, and they can be either cross state, the bar state. Cross state means here, suppose input signal, it is in the input port, lower input port, then it can be transferred to the upper output port. So, or input upper port can be transferred to the lower output port. So that is a cross state. Or it can be bar state, that here you can see input signals in the upper input port can be transferred to the upper output port, upper output port. That is the bar state. So it can be cross state on the bar state. So based on these things, you can see there can be two types of cross connect switches. Can be generic directive switches, or can be gate switches. One example is this, you see, that is directive switches. In this case, you see there are two wavegates are there, two wavegates separated with some interaction length, right? And two electrodes are placed on the two wavegates. These wavegates not. These are the actually. This is something like directional couplers. The optical wavegates. These are the two wavegates are there. Optical wavegates. And light couples, light is coupled, you see, into one waveguide, and that is divided into two, right? And I mean, here if the light, no, not divided into. This is not the 2x2 coupler. This is waveguide coupler. So here, when light is lodged into this one waveguide, then because of evanescent, you see it here, evanescent wave is there in the outside the core region. Similar, the energy can be coupled to the next ones through evanescent couplings. Of course, here the voltage also is a function of these couplings. If there is no voltage applied across these two electrodes, then you see it will be the cross state. Means the input signals will be in the couple port. This is throughput port. It's a couple port, right? But if you apply the voltage, then it will be in the bar state. Then in the upper port, you can have the signals, right? So actually, how it is being done? When you apply the voltage, actually that will change the propagation constant, beta. If you see, the propagation constants can be varied by applying the voltage. It will increase. So in this way, you can have the cross state and bar state. So cross state will be when zero voltage is applied, and the bar state you can have it when you apply the voltage. But here in this case, of course, here the important thing is this waveguide separation. Waveguide separation is important, right? And waveguide mode size. Also here, this interaction length is most critical, right? So to reduce these tolerances and having to get very good switching, you can use another configurations, that is reversed delta beta couplers. Here, same configuration is here, but here electrode is split into two. You can see one electrode, it is split into two, right? It is divided into two parts, right? And you see the voltage applied plus minus with two electrodes. So if you apply the equal and opposite voltages, then you can have equal or opposite voltages, then it will have the cross state. But if you no voltage is there, then you see it will be in the opposite phase. No, if you apply if you apply the voltage, same voltage, then it will be in the bar state. But if you apply the opposite voltages, then it will be in the cross state. So cross state and the bar state can be obtained using delta beta coupler and the voltage applied. So that is another switch of cross current elements. One more configuration is here. I mean, two more rather you can say directive switches using the interferometric setups. Here, very similar to Mach Zehnder interferometers. Here you can see there are two 2x2 coupler is here. There is one 2x2, another 2x2 coupler, and they are connected through waveguides. Two waveguides are there, and in these waveguides, electrodes are there where voltage is applied, and opposite voltages are applied. So in this case, you see it's a balanced bridge configurations, right? Interferometric, it is called balanced bridge interferometric switch configurations, right? Interferometric switch configurations. So here you see when light is incident here, it is divided into two parts. Here this coupler, so light will be divided into two parts. Right. And when no voltage is applied, the light enters into the second waveguide. You see second waveguide, and the second coupler, then it will act as a the same as in the first ones. So it will combine, and all the light will be transmitted in the cross state, lower port cross state, right? To achieve this bar state here, then you see at that times voltage will be applied, and that will change the phase of these two arms. So if the phase is 180 degree phase difference is here, then you can have the bar state. So bar state you can have it using the no voltage or voltage applied. So that means one case in the same phase will be there within the two signals, and in other case there will be opposite phase. And the opposite phase is there, then light will be transmitted in the upper port, upper gate. There can be another configurations when there is no, here you see between the two gate gap is the separation is here, but there can be intersecting also. Here this is useful, very useful for crosstalk. This is for crosstalk eliminations, crosstalk performance. These intersecting waveguide switches, right? Here you see in this case there is you see there is no separations, right? Here also by applying voltages, you can have voltage or no voltage, you can achieve the cross state and bar state. So with of course here the main advantage is here crosstalk can be eliminated. So other cases then little bit crosstalk will be here. And so we have seen this, the cross current elements can be two types, one is directive switches, another is the gate switches. Here you see the second category, it is the gate switches, where there will be a splitter is here. 1:n splitter is here, means when the input signal is coupled in one of the splitters, it will be divided into two, and then that those again there will be here these are the gates actually. The signal will pass through these gates, and then again there will be n:1 combiner. This is combiner. Just reverse of the splitter combiner. So first it will be divided into two, and then it will pass through the gates. These gate elements, they are called gate elements, can be amplifiers. We have seen the amplifiers. Semiconductor amplifiers can be amplifiers. So these are the amplifiers, right? Amplifiers. So by putting amplifier on and off, by varying the gains, we can select. I mean, in the we can have the switching effect. By switching effect can be realized by turning on and off of these gate elements. But the distinct advantage is here, since these are the amplifiers, so you can couple the coupling loss. You can compensate. You can compensate the coupling loss or splitters, etc. Splitting loss, etc. Those can be compensated using these amplifier gates. So these are the different switches. These are actually useful for circuit switching. For packet switching, of course, you see you need another type of switches are required for packet switchings. These switches are mostly used for the circuit switchings. And in the packet switchings, based on one example is you see contents and resolutions by delay lines. When you consider the packet switching, the problem will even the electronic packet switching. A problem is this: there can be collision of the packets. So in electronic switching, so these contention or collisions can be or packets can be overcome by buffering the packets. Suppose two packets, if they are supposed to deliver the common output port, then there can be collisions, there can be contentions. So that problem can be avoided in electronic domains by using buffers, right? But in optical domain, how buffer can be used? Because there is no electronic component here. Optical signal need optical buffer. So that is possible using delay lines. These delay lines means it can be a roll of fiber. The fiber will be, signal will be circulating. So there are certain times where the signal can be stored. Optical signal can be stored. So by using delay lines, the contention can be avoided. Contention can be avoided. So in this case. So here you can see it here, a series of the cross connect elements are there, right? And each delay lines as buffer. 2 by 2 cross connect elements are there. Number of cross connect elements are there. You see here, the 1, 2, 3 in this way. Number of cross connect elements will be there. Delay lines are used as buffer. So if the two packets, suppose it's a packet from this one and this one, supposed to deliver to the output port of these ones of this cross-cut element here. So collision might be there. And so to avoid that contention or collisions, then you see one of the packet, it is stored in these delay lines, right? So the delay lines. So one packet is switched to the output. The other one can be switched to the same output port when the first packet will transmit. Right. So by using delay lines, can be avoided. Contention can be avoided in this case. So and this is useful for photonic packet switchings. The modern day communication systems are based on these photonic packet switchings. For very high speed systems, you need this type of switchings. All optical switchings are equivalent. So this is the things. Another optical elements which most important is the wavelength converters. Sometimes you see, I'm showing one examples. Wavelength converter of why wavelength converter is required. You can see it here. Suppose switching elements are there. Network is there. The other stations are there. See, this is one stations. This is another stations. This is another station. This is another station. This is another station. So let us say this is A. This is A. This is B. This is B. This is C. This is D. And this is E. Right. This is A. So in this case, you can see it here. Suppose the light path is generally for transferring information from one station to another station, light path should be established. Suppose C to A, there the you see switching elements are there here. So here to here through the switching, this switching element S1, and the switching element is say S2 is there, right? S2. Now, say from A to C, it is A to C. C, it is through lambda ones. Say C to A. Let us say C to A. It is through lambda ones, right? And C2B, 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 that is say lambda 2. That is say lambda 2 and D2E, 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 say it is D2E, it is lambda 1. This is also lambda 1, this is lambda 1, but this is lambda 2, right? Now, suppose if station A wants to transmit information, suppose this is D2, D2E. So now, if say D wants to transmit information to A, you see here blocking will result because D2 D2A, not a single wavelength is here. From D2S2 switch, that is through lambda 1s. This is through lambda 1s. This is no, okay, no D2A. It is D2 D2B, D2B. Let us say D2B, right? D2B. D2B, if the D stations D, it wants to send information to B, then blocking will result because it is through lambda 1s after, but here there is no lambda 1 route here, like previous path is not there. So blocking will be there. So to avoid these ones, we need wavelength conversions. Wavelength conversion means information from one wavelength would be converted to the other wavelengths. And in fact, wavelength will not be converted. Information carrying in the one wavelength will be transferred to the another wavelength. That is called wavelength conversion. So though the term is used wavelength conversion, but actually information is transferred from one wavelength to the other wavelengths. I'll give you simple examples. You see it on the same way. If you see it another examples, say there are one node. This is another node. This is third node, right? So you can see it here. Suppose this is one node 1, node 2. This is node 1. This is node 2. This is node 3. So same thing. If you just see this is lambda 1, right? And this is node 2 to node 3. It is connected to lambda 2. Lambda 2. You see there. So you can see it here. So if the node 1 wants to send information to node 3, then blocking will result because you see the light path is available from node 1 to node 2 lambda 1s and node 2 to node 3 lambda 2. But you see same wavelength is not there. To transmit the information, you need same wavelengths. So that is not there. So it's not possible. But the same way, using wavelength conversion is possible. The same things, I mean, blocking can be avoided. If say here, if says information carrying signals, it is lambda 2, it is converted. Suppose lambda 1, it is available here. Then you see, if it is converted to lambda 1, this is lambda 2. And if it is wavelength conversion easier here, then you see information can be transferred from 1 to 3. So that is the wavelength conversion. Otherwise, blocking will result. So how this might happen? You see actual cases using semiconductor optical amplifiers. I mean, it can be used semiconductor optical amplifiers, semiconductor lasers, optical loop mirrors. So those things are there. Using those things, you can achieve the wavelength conversions. Wavelength conversion, I'm telling you, the information will be transferred from one wavelength to others. So using, say that can be, one example is cross phase modulations. It can be cross phase modulations. It can be what is the other things? Four-way mixing. Those things are there. One example is see quickly, and that is using Mach-Zehnder or Michelson configurations. Here, this is the Mach-Zehnder interferometer. Two semiconductor optical amplifiers are placed in asymmetric way, placed there. And you see here, this is the continuous wave signals, and this is the input signal which carries the informations. So here you can see it here. This semiconductor amplifier, the refractive index and gain can be modulated by the input signals, right? So initially, when the input signal is this can be co-directional or counter-directional. So here, this CW signal is launched from this side, and input signal is launched from this side. And you see, actually, signal will be transferred from lambda S to lambda C. Continuous wave signals. So here you can see it here. This light, when it's launched, this will modulate the characteristic gain and refractive index of these amplifiers. Next, when the continuous wave signal launched from this side, then you see when it passed to this through the amplifiers, then you see it will be modulated by this refractive index modulation and these refractive index and gains is the same things will be here, so that this wavelength will carry the same informations as the input signals. You see it here. This comparison can be also the Michelson right. I mean Michelson type. Here it is here actually here you can see it here. Here it is not a closed interferometer, it is an open interferometer. Here continuous signal is launched from this side, and you see it here. Actually, there is a return path will be there. This one mirror here. Signal light is propagating from this side, right? And this is the reference arm. Here one is Mach-Zehnder, one is two arms, one is called signal arm, reference arm. Two arms are there. Here are also two arms, but it is not closed. So this is Mach-Zehnder type interferometer. This is Michelson type interferometers. The signal is applied from this side, and continuous wave signal applies continuous wave where the information will be converted in lambda C. This is you see it here. First, it will modulate these two semiconductor optical amplifiers, and when this signal will propagate through these semiconductor amplifiers, it will carry the same information as the input signals. So these are the different configurations for wavelength conversions. Next time also we'll see it a little bit easier in cross phase modulations. Next time we'll see it. किसी का कोई क्वेश्चन है तो पूछो. हम तुम पता किसी को कोई क्वेश्चन नहीं है, फिर भी मेरा पूछना है, बोले अमल कुछ क्वेश्चन है? अगर सुन रहा है तो बोलो, कुछ क्वेश्चन है कि नहीं? क्वेश्चन है अमल? बाकी तो कोई आंसर नहीं करेगा. कोई क्वेश्चन है अमल? अनम्यूट करो.
नो सर, नो सर.
और क्विज का फिर कोई हर्षवर्धन से डिस्कस कर लेना. फिर कोई ऐसे तो क्विज होगा फ्राइडे कब देना चाहते हो? तो हर्षवर्धन नहीं है. कितना बजे? आफ्टर 5:30 कौन टाइम सुटेबल है? आफ्टर 5:30
we will decide and tell you.
तो tomorrow you just inform me.
Okay sir.
Tomorrow inform me about the time of the fourth quiz, as well as tomorrow also will tell me the date and date for the fifth quiz.
Okay sir.
To remove some of the guys, I have to remove from the teams. They will discuss the HODs, then they will enter. Otherwise, they will be removed from the meetings.